Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello everybody. How are you all doing? To another episode of Ask Us Anything About Electrochemistry. I'm your host, Dr. Alex Paroff. Thanks to my colleague, Dr. Neil Spinner. Before we actually get into the, I'll go through the boilerplate stuff first.
Yeah, that's probably a good idea.
So we get a lot of questions. We're two chemists at Pine Research Instrumentation, and we get lots of questions either through mail, webinars, YouTube videos, just tons of technical questions about electrochemistry. And sometimes it's not always the best or most appropriate time to answer those questions. So we created this designated live stream specifically for answering some of your technical questions about electrochemistry. So we are using Restream as kind of the platform for posting this, and now we're live streaming to both YouTube and Twitter. So if you're on Twitter, let us know. We're really excited to have you. And so during this live stream, you can ask any questions you want in the chat. We're going to try to get to you as soon as possible. If you're a tier 1 or tier 2 YouTube member, we tend to prioritize member questions first. Also, if you're a tier 1 or tier 2 member, you should be able to even join us on Restream, so you can either share your screen, share the data, and then we can actually have a conversation rather than just typing or chatting.
That code's still there?
I think that code is still there.
Yeah, we haven't changed it.
Yes, we haven't changed it. There is
Cool.
not anything
Join
crazy.
us.
We typically find there's maybe like a 20-second delay between when you write something and when we actually see it and say something. So just keep that in mind if we don't get to your question immediately. And plus, there's usually a backlog. Now we have a backlog of questions. But also, you can ask any question you want. We have found in our time that the more information you give us about the question, the more detail, the better. If it's just a very generic question, sometimes it's a little hard for us to answer because it can be so big, the answer. And because names come in from YouTube and from other countries and stuff, if we mispronounce your name when trying to answer your question, please forgive us. I think those are all the main kind of boilerplate things we do before we do the stream. Generally, one last thing. If you're watching this after the live stream, come back a few days later. We will have in the timestamp lots of the description in the description of the video. There will be timestamps for all the questions that were asked if you're looking for your question. Okay, and so we actually have a very special announcement. We've been working on something, and before we get into answering your questions, which we will, Neil, do you want to share this video?
Yes, I do, and I will add that my esteemed colleague Alex here put this together, and both of us appear in it, and it's brilliant. So enjoy, everybody.
Yeah. All right. Yes, everybody. We are launching a podcast, the
That's right.
Electrochemistry Podcast. If you are a tier 1 or tier 2, or actually if you're a tier 2 member, you will have early access to it January 7th. And then we're going to have a public release on January 4th, 2024. So Neil and I have been working on this for a long time. We're basically done. We have very minor edits. And December for early access. If you want to listen to us, if you're driving or on your commute or whatever, if you're working in the lab and you want to listen to something,
If you're stuck polishing an electrode for the next 35 to 40 minutes,
Yeah.
and you could listen to music or watch like a Netflix documentary, you should instead listen to us because we're part of a media empire and we're taking over.
yeah, that's
coming to earbuds near you.
Yeah. So hopefully we'll have more information about it later, but it's something to look forward to. We're
Yeah.
pretty excited. All right, let's answer some questions. We got lots of
Let's
questions.
do it. Okay. So the first is a series of questions from Kleber. It looks like high ductors. I like that because of the duck. And
Yes.
that's our company thing. I'm working with voltammetric oxidation of tricyclic antidepressant using laser-induced graphene electrode. Say that 5 times fast.
Yeah.
This working electrode is highly hydrophobic and a surface air layer is formed. Can you guys please give ideas of supporting electrolytes that I could use to break the superficial tension and improve the contact solution of the working electrode? So it looks like Chris, our resident honorary PhD live streamer with us
Yes.
here, was talking about surfactants and asking about some of the reactions. It looks like that Kleber clarified you're working at anodic potential, and there's an oxidation of, I don't know what this is, carbamazepine and amitriptyline. Okay. And so it looks like Chris was actually sort of leading towards some of these thoughts that I was going to suggest. Essentially, how could you do this? Oh yeah, sorry. The last bit was that you filled in not yet. I just tried some aqueous buffer solutions, phosphate buffer 7 and Britton Robinson pH 1 to pH 9. So my thoughts about this are twofold. The first is the use of a surfactant, of course, would break surface tension. The problem is that some surfactants may be electrochemically active. And so I think that's what Chris was talking about. You can correct me if I'm wrong, Chris, but something along the lines of like, okay, I use a surfactant like soap. Just the simplest, the dumbest example. You wouldn't use like detergent. I'm just thinking of anything that breaks the surface tension, right? That could, in theory, help with the hydrophobicity of your catalyst. And this is quite normal. Like yours is probably highly hydrophobic, but carbon is intrinsically hydrophobic. Okay, so the problem, of course, is that if you go to especially since you're at oxidizing potentials, probably the surfactants are organic compounds that may be oxidized at a high enough potential. And especially if you're going to 1 volt, it's at least probable, or at least possible, I should say, and maybe probable that you would have some side reactions of your surfactant. So you don't want that. So that's bad. And then the only other thing I could say is that you might have to use a sort of auxiliary electrolyte or a mixture, like people typically cut water with alcohol or some other what polar aprotic solvent, basically, that cuts the surface tension. Like alcohol has a much lower surface tension than water. Water has a very high surface tension, and it's the hydro and hydrophobic. So so if you might have to use like methanol or ethanol or something, isopropanol, acetone, other than going to a straight non-aqueous solvent that might work better, like acetonitrile. You might try cutting with some of those solvents and see if that helps. I assume that the electrode-electrolyte interface is compromised in some way because of the extreme hydrophobicity. And so some of these things could potentially help you.
Yeah. One thing, if you do decide to go the surfactant route, when I was a graduate student, one thing that we used in lab was Tritinex methanol.
Oh, interesting.
So you need a really, really tiny, like we would make like maybe, I even forgot. It was like 1% Tritinex methanol. And it was like 1% in this huge methanol, like 100 milliliters of methanol. And then we would use like a drop of that. So it was like almost a a 2-factor 100x dilution of this Triton X methanol, and it would break the surface tension. So instead of getting that hydrophobicity, you'd have some. It would be hydrophilic with the surface. So I'll just type that in the
Triton X methanol.
Triton X.
I have no experience with Triton X methanol.
Yeah, it's this weird kind of it's a cell lysis detergent, apparent according to Thermo Fisher, but that might be an option, and that will hopefully it doesn't like cake on the surface in such a way that like it blocks the electrode or does a reaction or anything like that. Something to try. Something that might help. So let us know if you have any further questions, Kleber. But maybe that's at least an idea to go forward.
Looks like we have Chatelier Paul asks, hello, how can evaluate the conductivity by EIS? So there's a couple of ways. I think we talked about this last week. I feel like this came up last week.
Yeah.
The quickest and most simple but possibly inaccurate way to do it. I shouldn't say it's okay. Basically, if you think about impedance, its units are ohms, right? And effectively 1 over ohms is conductivity. So in some sense, quite literally, you get impedance and you just take the reciprocal, and that's a conductivity. Now, what impedance, what frequency, like there's a lot of open questions here. Effectively, as a very quick method, if you can identify the, let's say the frequency range that you are of most of interest, like usually, let's say it's the conductivity of your, again, you didn't really specify what the conductivity of, right? So let's just say you're trying to figure out the conductivity of your electrolyte, like the uncompensated resistance, blah, blah, something like that. Then it's probably like a relatively high frequency. Let's say the frequency where the phase angle is closest to 0, then just take 1 over the impedance, the magnitude of the impedance at that point. That's a rough and dirty estimate of conductivity. Okay. Yeah. Now, a perhaps more rigorous way involves one of 2 other things I'll mention, which is there's the expression of with a length. So it's like people use. Let me share, and I'll have to remind myself. So, am I good?
Yep, you're good.
Okay, good. So, for example, start drawing. There it is. So there's sometimes conductivity is referred to as sigma, and it's sometimes used with this expression. And so this is L over RA, right? So what I just sort of advocated for as a variant was basically sigma is just sort of like 1 over R, right? And so this is 1 over ohms, and this is in the units of Siemens, right? And this is R is in the unit of ohms. Okay. But typically people will do something like they want it Siemens per centimeter or something like that, right? And the reciprocal of that, right, is ohm centimeters, right? 1 over Siemens per centimeter is ohms centimeters. So these are just units you'll see. Sometimes it's ohm centimeters squared. I'm just sort of mentioning all these things because there's a variety of what people mean when they talk about conductivity, and I don't know exactly what you mean, and I don't know 100% why everyone chooses one or the other. It's a bit opaque to me, to be perfectly honest, why one is more important than the other, why you have per centimeter or centimeter squared, if it's per area, like what length are we talking about? That's all somewhat nebulous. The point is that typically this is some kind of characteristic length. So for example, it might be the diameter. It could be like the thickness of your sample. It's not clear. I don't exactly know what it is supposed to be. And nobody really seems to know from what I can tell. There doesn't seem to be consensus when you find papers that people, they pick a characteristic length and it's like, okay, well, great. That's what I'm picking for my system. And then typically A is a little more straightforward. That's the exposed surface area. But this is the same resistance that you would get from impedance. So this is perhaps a more rigorous, I don't know, way to get the conductivity from an impedance value when you get the resistance. What resistance is it? Of course, that's the same thing I just described. Well, I guess it would be high frequency resistance unless you're talking about a different conductivity or something like that. And then the last thing I'll mention is that a way that this is sometimes obtained, let's say you have a flat surface, like a flat membrane. You typically see people do 4 electrode experiments where they have sense line 1 and sense line 2. So this might be reference and working sense. And then they have drive line 1 and drive line 2. So this will be like working drive and counter electrode. And then you do your impedance this way. And so this might be your L. So this is a little more straightforward. There you have an L. This is what's done with for like membrane conductivity calculations. This is pretty common. Sometimes this is done with like a Lugan capillary cell. There's a version of this where like you sandwich a membrane in between, you put Lugan capillaries very close and reference sense lines, drive them very, very close, minimize that distance, do impedance at high frequency, or you can do a CV over a very narrow range and you just get a Ohm's law, like V equals IR, right? You get a slope, whether V or I is either way, whatever. And then that slope here, right? You just use our Ohm's law, you can get your resistance. So there's a number of ways to do that. That's obviously not an impedance method, which is what you asked about. I'm just saying these are different ways to get that R, which you can then plug into this expression and get your conductivity. So there's a little bit of just abstract, I guess, semi-specific information about where impedance and conductivity connect and relate to each other.
Nice. So we do have a follow-up. I do want to mention first, Sampana, I will be going to Gothenburg. I hope to see you at the ECS meeting. Should be fun. But then stop by the Pine Research booth. Shameless plug. Chatelier Paul is also asking, just kind of a follow-up. Do I have to fit an equivalent circuit for EIS so that you get R? And then I guess a follow-up question is R is like the series resistance?
Yeah. So I will elaborate on that a little bit because I said something to that effect, but it was a bit of a throwaway. So let me be a little more clear. So if I have a Nyquist plot and I have something like this, and the corresponding Bode plot might look something like, let's say this is blue side is the phase angle. This is 0. This is minus 90. Okay. It might have something that looks like this. That's what the Bode plot might look like. And then let's say this is the impedance magnitude. Just for good measure, I'll just draw that. It might be like something like that. Whatever. I might have drawn too many plateaus. It doesn't matter. The point is that of the options you have 2. One is you could fit this to a circuit, like you said. You could fit the whole data to something, okay, whatever, just your typical circuit. And then it's either this resistor or this resistor. It kind of depends. What are you trying to get the conductivity of? Like this is more like your solution on compensated resistance. This is more, R2 is more like your charge transfer resistance. If you want to know the conductivity of related to the charge transfer process for your Faraday reaction, just so to speak, maybe that's the one you want. I was thinking more likely this is the one that you're concerned with. So, but yes, you can do a circuit fit and get the value for this that way. The other way is that, like I said before, and I kind of threw this away here, but basically this is the point right here where the phase angle is closest to 0. It's usually at high frequency. It might not be the highest frequency because there'll be a little artifacts or whatever at like 1 megahertz, let's just say. So this point's probably in the kilohertz, hundreds of kilohertz range, tens of kilohertz or something. But whatever the corresponding Z magnitude is, this Z magnitude, that can be your R. Because that is actually effectively what this R is. It's basically the same. These two are roughly equivalent. And your circuit fit would bear that out. So that's a quicker way to do this if you don't really want to do a circuit fit. If you just do a short impedance experiment, and you don't even have to go down this frequency, you can just do like just this part here. You can just do a few high frequencies, find the point Z magnitude where the phase angle is closest to 0. That's roughly a fully resistive process. That's what that means. If the phase angle is close to 0, it means there's basically no capacitive interfering processes. You basically have a purely resistive situation, and that's the resistor. That's the resistance value or the impedance value that you can correlate to conductivity.
That's good. I am trying to look up Jagannath is asking how to measure the cyclic stability in electrochemical workstation. And Jagannath, I guess I maybe have questions about clarification. Maybe I don't understand the question enough. I can interpret this two ways. Cyclic stability can be like, so first off, electrochemical workstation is basically a potentiostat, right? It's the instrument that you're using. You can measure the cyclic stability of a device like a supercapacitor or capacitor or a system, how stable it is as you cycle, charge, discharge, a battery or something like that. Or are you looking for, when you're doing an experiment, how do you make the instrument more stable? Because sometimes it's not uncommon that potentiostats will oscillate. They'll cause oscillations in just this, like, as you're sweeping and the potential is adjusting or switching, you'll see these oscillations, and that is also a stability issue. So please, if you could clarify a little bit more, if you're referring to potentiostat operation, or do you mean cyclic stability as an experimental test to a system, and how a potentiostat would do something like that? So that's that's the kind of the clarification I like about the question. Hopefully that makes sense.
I have also the same amount of confusedness reading the question. I don't understand. So yeah, please clarify. We'll try to answer once you do. Before we dive into potentiostat stability, if that isn't really what you're thinking about, right. like filter settings or all these kinds of things, which we can drone on about, but we won't if that isn't exactly what you mean. So, Race is back. Nice to see you again, Race. Let's see. We have a question. What is a charge transfer resistance in lithium-ion batteries, in your opinion? What is charge transfer resistance? Do you consider interfaces between electrode, electrolyte, and SEI layer? Yeah, basically, charge transfer resistance specifically in a lithium-ion battery is probably referring to the actual process of charging or discharging the battery. That's one of 3 different processes, generally speaking. And I always forget one of them. Is intercalation is one of them. That's the most common one, which is where, like, lithium, you have like a carbon, usually a carbon 6, and you get like LiC6. And so it's like lithium is intercalating into the lattice of your graphite, for example, or your NMC cathode or whatever. It's an intercalation, deintercalation process. That's what it is. Otherwise, it's a decomposition. So sometimes it's like semiconductors and like metal oxides do this. It's actually a decomposition into other products, and then a recomposition. That's not a word.
Recomposition.
Decomposition. Whatever. Reformation. I guess. I don't know. Whatever. Anyway, decomposition, intercalation, and then I swear I can never remember that there's another process, and I don't remember what it's called. There's another one, but that's what it is. So
there's no actual like electron transfer.
No, there's electron transfer. It is both. It's the charging, compose, decompose. So the decomposition and then the composition. Thank you, Chris. That would be the appropriate terminology. But no, it's a redox process for sure. But like lithium, X lithium plus 6C, this is ions, plus X electron, something like this. I'm sort of butchering a little bit of exactly how it works. Gives you LiXC6. So this is like the carbon, sort of the carbon reaction. Basically, the full, if X is 1, that's like a full intercalation. But this is what an intercalation reaction essentially is. And then a decomposition reaction, and I'm going to try to do this on the fly, and I'm going to probably mess it up badly, but here we go. So like nickel oxide, this is what I worked with when I was in graduate school. Nickel oxide plus lithium. I'll have to balance it afterwards because I don't remember exactly how many. It gives you Li2O. So there must be 2 of these and 2 of these. Plus, I guess, nickel. Must be elemental nickel. Yeah, because that's 2 Lis. Yeah, something like that. So it's a redox process, but it's this literally decomposes into elemental nickel and Li2O, and then when you go back, I'm droning a little more about this specifically, but this is one of the problems with Li2O is not very conductive, so it's hard to go back. It's easier to go this way, blah, blah, blah. But these are, and then there's another, it's like a substitution maybe. I knew this like down pat when I was in graduate school, and I was doing this all the time, and now I'm like pathetic and I can't remember the
Nah, it happens to the best of
The
us.
point is that, to your question, what is the charge transfer resistance? It's related to that process. That at least most probably when you're talking about a charge transfer resistance, you're talking about something like that. Now, it also could refer to transfer of charge between these layers of electrode, electrolyte, and SCI. That is possible as well. And there are certainly, when you do impedance on a battery, you get usually in order responses at high frequency from the SCI, and then the anode, and then the cathode. And so you actually are probing those layers, I'd say, specifically. And, as I've drawn many times, it's like you can draw, for example, a bunch of Randall's elements. You can draw an embedded Randall's elements, and those are interfaces. And sometimes you're talking about like the SCI or the it's sort of unclear to me, I guess I would say, exactly whether you're talking about the SCI itself or the reaction of the SCI with the anode current collector, or there's some nebulous definitions here. But I guess the most direct answer is what I previously just said, which is that I would generally say the charge transfer resistance is that process, whatever that process happens to be for your material you're studying. It's the charge transfer, intercalation, or decomposition, or whatever the third one is. I think it's substitution. Substitution reaction.
Okay.
Substitution reaction.
Kind of moving down the list.
You answer that while I try to figure out if that's what it is.
So from Raj Paul saying, why we observe still current is there a switching potential in cyclic voltammetry? So Raj Paul, just because are you talking about still current as a type of current, or just a little bit more clarification on what you mean by still current? Why do we observe still current? And yes, there is a switch. So in cyclic voltammetry, you switch the potential. You start from some initial potential. You have a final potential, which may be the same point. But as you sweep from one point to another, you're going to switch the potential, right? So somebody switch it and then sweep it back. So there is a switching potential in cyclic voltammetry. So maybe the current that you measure, I mean, there's all kinds of currents in cyclic voltammetry depending on where you start and stop the voltammogram. Yeah, so let me draw that. Let me actually, I'll share my screens, hopefully. And of course, please let me know if you have, hold on. Oh, okay. So again, let me know.
And I'll just say, Jagannath, I see that you clarified. I'll get to your question in just a moment.
Yeah. So if you're doing you can see the PowerPoint, right?
Yes. You're good.
Okay.
You're good.
So the applied waveform you have voltage versus time. Might look something like this. This right here is the switching potential in CV. So it's switching. Potential. And then, of course, you measure the corresponding voltammogram, which is in current. You measure the current as a function of the voltage. So there's always a lot of questions, like maybe 0 is here, but you have a non-zero value here at the switching potential, and it's because there's a lot of processes that are going on. There's even potentials, like depending on where you start, like maybe if you start here, maybe this is where you actually start your cyclic voltammetry experiment. Well, maybe there's some kind of current. There may always be some kind of current or some kind of process happening, even if the potential is 0, and especially if the potential is non-zero, there's going to be current that's going to be flowing, and it can be associated with a variety of different things. So one thing some people get confused about is, well, why is the current like some people never really know, like, okay, the current is going down here, but remember, this current is still associated with, like, if this is an oxidation reaction, this is associated with an oxidation reaction. So that's, this current is actually just, if we were to continue this voltammogram, this current would flow this way, and it's just flipping this the other direction. That's what's actually happening if you were to go further out in time. This is a change in time. But hopefully that makes a little bit of sense. And if you ask us more questions, just kind of clarifying this idea, I'm happy. We're happy to help. All right. So Jagannath gave us some additional clarification. So yes, this is the life cycle of a supercapacitor, right? So this is how do you measure the cyclic stability of a supercapacitor using a potentiostat? That's really what the question comes down to. And
yeah, so I mean, that is basically, at least a lot of the times to my knowledge, a supercapacitor test involves doing CV a million times. So supercapacitors, unlike batteries, are charge-discharge, which are both charge storage devices, but supercapacitors are extremely rapid charge and discharge devices, whereas batteries are slow, usually charge and discharge devices, right? They provide a capacitor provides a quick burst of energy over a short amount of time. A battery provides a slower amount of energy over a longer period of time. Generally, of course, there's variations on both of those, but a cyclic stability test of a supercapacitor might literally just consist of doing CV back and forth like this times 1,000. Just back and forth. If this is a CV, this is voltage and this is current, you find a place, voltage limits, where you have basically a rectangle almost. It's just an envelope. And there's no Faraday processes. There's no peaks, right? Nothing like that. Nothing like Alex just drew, basically, because you want the non-Faraday capacitance, which is what the supercapacitor is good for, right? And you're basically just monitoring what its progression or what it does, basically, which effectively the current, like half of the current here, this current, the capacitance is equal to. You always have to correct me on this. Is it current times scan rate, or is it current over scan rate? What is it?
It's so the current
millivolts.
The current is equal to the capacitance times the scan rate.
Current is equal to capacitance times scan rate.
So that means
capacitance is equal to current
divided by the scan rate,
because that's amps over volts per second, and that's coulombs per volt, which is a farad. I'm like way off the screen. I'm off the screen.
You get farads though.
Yeah. Amps seconds is a coulomb. Coulomb per volt is a farad. Yes, we did it.
We
Okay.
did it.
So yeah, I don't know why I lack the intelligence to remember this simple equation for some reason. I always write
No,
it
it's all
backwards.
good.
I just can't remember it. Anyway, the point is that you can basically monitor your capacitance change over time, and just however you can do, like, you make a plot of like cycle, number up to 1,000 and like capacitance or whatever, and you see like, oh, look, it's getting worse over time or whatever. So that's probably the most general kind of a way that you would do something like that. And there's probably other ways to do it. There might be other methodologies, but that's the simplest that I can think of, basically.
Yeah.
So let's see. Was there any?
There's some follow-up
Some
from
follow-ups
other
for-
questions.
Okay, yeah, no problem.
But there's also like some new questions,
Okay.
and I think
Azaz has a question. Is that the next one?
yeah. So Zaz has a question, which is just to explain the principles behind fuel cells and their potential as clean energy sources.
Oh,
I know
man, I have a
you-
cool animation for this.
Oh yeah,
I should
yeah.
show that. Hang on, I'll pull that up.
I think that was it was one of your webinars.
Yeah, it's an advanced fitting one. I did.
Yeah, it was advanced fitting one.
I'll pull up the master because I have it in here.
That one's very good. If you want, I can try to answer another question while you look for that.
I think I found it. Why don't you answer another question?
Sure,
Just to
sure.
Make sure I know it.
So Azaz or Azaz, we'll get back to you in just a moment. I think I can answer a relatively quick question from AFSI Analysis. If CV started at non-zero, and actually this is related a little bit to Raj Paul's question. So if CV started at non-zero, suppose from 0.6 volts to 1.2 volts with a perfect duct shape, what does this mean? So so if I just kind of share my screen, and then we actually don't have to do too much different here. I'm just actually going to erase a couple things so that it's a little bit easier to see. But what you just described, or what you just said, was basically, oh, I started at 0. Let's say this is 0.6 and this is 1.2, and you get this voltammogram, right? This is a perfect duct. These types of duct-shaped voltammograms are associated with some kind of typically single, maybe two, but really single electron transfer processes that are homogeneous in nature. So you have the shape has to do with the diffusion of a molecule towards the electrode surface. So if I have an electrode, weird shaped electrode, and I have some kind of some analyte A, there is a current associated with, say, the oxidation, which is here. I'll just highlight that in green. So there's some current associated with the oxidation of A. And if we go back, so that means A is losing an electron. And this process continues to happen until we sweep back, and then eventually we reduce. The electrons go back to A near the surface. And so, yeah, that's kind of what you're measuring. Other experiments that people typically do is they'll do a scan rate dependence. So they will they'll actually change the scan rate. They will continue to change the scan rate, adjust the scan rate. And then you'll notice that, like, oh, you have a different one and the current gets higher. You have another one, the current gets higher. I mean, it's not going to look this messy, but you kind of get my drift. But you'll do a scan rate study. You'll look at the peak current as a function of the square root of the scan rate, and if you do that, you should get a straight line, square root of the scan rate, current. This is indicative of the Randall-Sebzage equation. And that means you have a homogeneous diffusion-controlled species in solution. So those are that's kind of like the meaning, sort of say, behind like getting a perfect duct, what that means, what it does. That's at least a relatively quick answer. So hopefully that was helpful. And if you want further clarification, please let me know. Did you want to show?
Yeah, I do have it ready now.
Yeah, so this is going back to Aziz's question.
Please explain the principles behind fuel cells. So yeah, so I'll describe it. I'll try not to be too long-winded because it is a bit of a complicated topic for sure. But so I have a slide on how a PEM fuel cell works. Let me know if this is sharing. Is this working?
Yeah, it should
How
be.
do I?
So do you have it on full screen?
That's it. Is it sharing the whole thing here, like
Yeah.
animation?
Is there an animation?
Yeah. Is it animating?
It's not animating. Why?
Hang on. Stop sharing. Let me see if I can. Why won't it animate? I mean, it's animating on my screen. At least it was.
Yeah.
I wonder. Entire screen. I'll just share my entire screen. Does that work?
So nothing's coming up right now. Okay.
Is the entire screen sharing?
Yeah. So okay, now the entire screen is sharing. It looks like it. Yeah. Okay. Now it's animating.
Is
It's
it
good.
okay?
It's
so you're
animating.
seeing it. All right. So briefly, this is how a fuel cell operates or
Yeah.
is constructed. Okay, you have an anode and a cathode separated by a membrane. Anode and cathode are usually both platinum on carbon. Practically, what it is usually is it's a piece of carbon paper, a very thin piece of carbon with platinum sputtered on it somehow, painted, sprayed, electrodeposited, zapped, ALD, something. There's just a bunch of platinum on it, and there's carbon there. Sometimes it's actually sprayed directly onto the membrane. And the membrane is usually something like Nafion, which is basically a proton shuttle, and I'll show you why. You flow hydrogen, usually humidified, there's water, there might be a carrier gas, but basically hydrogen goes on the anode side. The reaction at the anode is basically splitting up hydrogen into protons and electrons, okay? Protons go through the membrane from the anode to the cathode. Electrons go through an external circuit and meet up at the other side. That's where your electricity comes from. That's the actually power generation. On the cathode side, you flow air or oxygen. Again, usually humidified, sometimes a carrier gas, something like that. The reaction at the cathode side is the oxygen reduction reaction, the ORR. This is why people are studying ORR so much, because of these two reactions, the cathode is the one that's worse, it's slower, it's rate limiting. And so there isn't a lot, generally speaking, that we have to do as scientists to improve this anode reaction. Splitting hydrogen is relatively easy, quick, favored. But the oxygen reduction reaction has a bunch of problems associated with it, generally speaking. And so that's why everybody's studying it. Okay. But the reaction with the oxygen reduction is that these electrons and those protons get together with oxygen and make water. Okay. That is, in a nutshell, how a PEM fuel cell works. Now, of course, there's a lot of other kinds of fuel cells, but they all typically operate with a similar phenomenon. Some fuel, in this case, hydrogen, is provided, ripped apart. You get electricity, you get some ion. The ions travel internally. The electricity travels externally to power whatever you're trying to power. And they combine at the other end to make some product. Sometimes this produces energy, as in this case, which is why it's an energy device to provide you energy. It will naturally and thermodynamically provide energy for you. In other cases, there are electrolyzers, which operate basically the reverse of that. So you can supply water, you can provide energy into the system, rip water apart, and get hydrogen gas. So this is like an electrolysis system. This is called an electrolyzer. And this is basically a backwards fuel cell, in essence, that you could think of. It requires energy, but you get a product. Now, the product of the fuel cell is water. And so the other part of your question is briefly, let me get back here, is why are they like attractive or something like that?
Yeah, clean energy.
Why are they clean? Yeah, so
energy sources.
they're clean energy, quote unquote, because it takes in hydrogen gas and produces water. There's no carbon involved. Of course, that's not entirely true because materials require synthesis. You have to get platinum from somewhere. It's not as clean as exactly as you would say, but the theory of it is that it is an energy source that relies purely on hydrogen gas, which is tremendously energy dense, right? Hydrogen gas is very, very dense in energy. And the byproduct is not a pollutant in any way, shape, or form. It's water, right? So from that perspective, it's very, very attractive. And it's also quite efficient. It can be quite efficient. Now, we're working on. That's what scientists are working on, have been working on forever. Can we get it more efficient? Can we get catalysts that don't deactivate faster? There's a million and a half things, as you could imagine, working on fuel cells as with any other electrochemical technology. But hopefully that's a very short overview, skipping 1,000 steps, of course, just for time and for the purposes of this live stream. That is briefly how they work and why they are attractive for clean energy sources.
Okay.
So
I think that was a great answer, and your animation is very good. I
had
just
fun
think it's a
putting
really
that
good
together.
animation.
I like those.
So just kind of moving on, going to like the next thing. Well, if we have it, please remind us if we haven't gotten to your question. But S. Matt, who we do know, you sent us a question.
You sent questions
earlier.
just before, so
we didn't know if you were still on.
Yeah, thank you for bringing this up. So you said, is it recommended? I'll just bring up the questions you asked before because they were like 3-part, but it's a similar thing. You said, I'm designing my impedance for a PEM fuel cell, which is what I just talked about. Very timely. And so the questions are, at this point, I know what I can possibly use for this, like a pseudo-random binary sequence, which apparently is what PRBS stands for. A pseudo-random binary sequence signal in combination with morlet wavelet to calculate the difference impedances of the stack itself. And so the question was, you're wondering if you had some other findings or theories that may be important to apply better ways for calculating the impedance of a stack, multiple frequencies at a short time. So first of all, I don't have a ton of knowledge. Number one, to your question you just asked here, to again, just rephrase, I don't have a ton of knowledge really, which is to say basically any knowledge of pseudo-random binary sequences or morlet wavelets. Morlet wavelets, morlet. I don't know exactly how it's pronounced. I don't really know much about that. What I will say is that from what I can tell very briefly is that these are like short pulses, perhaps with like attenuated, like increased and then attenuated wavelengths, something like something like, as best I can tell, what this is like is something like when you provide a wavelength and it grows and then shrinks, something like that. You can correct me if I'm wrong, but I think it's something. So it's like I don't know if the like frequency is changing as well, you know what I mean, or it's just the amplitude. Like I don't know exactly, but it's basically some sort of like modified sinusoidal input, and maybe that's what the pseudo-random part of it is. So that could be part of what I don't fully know or fully understand, I would say. To that point though, what I would say is that I sort of fundamentally disagree with the characterization of this as impedance. It's not. Impedance requires a steady state, linear, causal, stable system, and this is not. Now that doesn't mean you're not getting information. That doesn't mean you're not probing your system in an interesting way. It's not really impedance though. It's just not. It doesn't qualify under the definition of impedance. That being said, it may be an interesting way to obtain a state of health of your stack at different times. As far as whether the PRBS helps predict some of these, I have no idea. I really don't. I only know that, for example, at like moderate to high frequencies, you can usually get some kind of an empirical correlation from EIS data, whether it's this kind of morlet wavelet thing or it's actual impedance data. You can get like equivalent parameters like the magnitude of the impedance or the imaginary impedance, the real, the phase angle, whatever, like impedance parameters. You can extract those and correlate those with states of health of your stack, like what its temperature is, what its, I don't know, what its power output is, get a brief impedance blast and see what you get. Like there might be correlations you can make like empirically with that. I don't know how you go down the impedance route because it isn't really strictly impedance. So I don't know like if any sort of like circuit analysis will be appropriate, because it's not fundamentally impedance. Like all of that might break down to a certain extent. And so I think it's perfectly reasonable. I think it's probably pretty interesting that you might be able to get some empirical relationships. And I don't really know fundamentally the answer to your question about whether that technique is recommended or not. I don't know. But that's the best that I can kind of answer that, is that I do have experience with this sort of empiricism of short impedance bursts at different conditions. That is a valid way of probing a system. It's a pretty useful way of probing a system because it's very non-invasive and it's very quick.
So following up with AFSI analysis, we've had a little bit of conversation, and then you've answered some of the questions about, you're getting this kind of current, what I believe to be current saturation at 0 volts, but then when you shift to 0.6 volts, I guess it sounds like it's normal, and then you're able to get a normal looking voltammogram. So there are a couple things to consider without knowing everything about your system. Here are a couple things to keep in mind. I should be sharing. So one thing to keep in mind with all of these is your voltage range and the reference electrode that you're using. So so you should have some kind of voltage range, and this is kind of a thing you may have seen or heard of, but it's like we typically use something like the H plus, hydrogen redox couple is like 0 volts, and that's a reference electrode. And then when you move, I just remember, I mostly remember like silver chloride is here. It's like plus 1, plus basically plus 0.2 volts is the silver chloride redox. Oh, sorry, this is C. Let me erase that. But the point is, you have a reference electrode. You have some reference electrode, and that has a potential that's shifted. And you have some redox processes that are happening. So I'm going to take a guess or stab at what your cyclic voltammogram looks like. This is just what I guess. So when you're at 0, your current starts to do this, and zero current is here. It's here, and then once we reach about here, this is this is 0.6, and then maybe I actually get rid of that and make it a little bit clearer. This is where you have kind of 0 current. And then you do your normal voltammogram, and then I don't know what direction your system goes in, but my guess is maybe it goes like this, maybe it goes like so, and then it goes up like so, or something like that. It's just a guess, right? So, and then here is that's plus 1.2 volts. So if you have a non-zero current at 0, that's very large. That kind of indicates to me that you have a good concentration of some species that is oxidizing. So I'm assuming that positive current refers to that. So I'm assuming this is the type of voltammogram that you're getting. Okay, all right, yeah, so I'm getting some feedback. All right, yes, this is what you get. All right, so what this suggests to me is there's some redox species. It could even be water or solvent or the electrode itself that is getting oxidized, right? So this thing is getting oxidized it's strange that it's getting oxidized at this potential, because it should continue to be oxidized. So maybe it might look a little bit more like this. It might be coming from the bottom rather than the top, because this is like a reduction reaction that's going on here. So again, there may be some levels of clarification to figure out what's going on, but usually this indicates some kind of maybe solvent or redox species is already getting oxidized or reduced. Now, sometimes one of the easiest and kind of simplest examples you could create this type of system or this kind of situation is if you have, let's say you get ferrocene, right? So let's say you get ferrocene, you buy ferrocene, you put it into your solution, and ferrocene gets oxidized. So you start at a reducing potential, and then you oxidize it, and then you get a normal voltammogram. But you might also buy ferrocenium like in a bottle, right? You can buy the +2 or +3 versions of certain redox species. And if you have the wrong version, if you have the +2 or instead of the +3, so if you buy ferrocenium and you start at a negative potential, your potentiostat's going to instantly start oxidizing it. Instantly start reducing it back to ferrocene. Your voltammeter is going to start at a high non-zero current. That's one thing that happens, and I have made that mistake many times where it's like, do I have the ferrocyanide? Did they buy me ferricyanide? I don't remember. So that, sometimes that happens. But if it's happening at 0 and you're moving to a positive potential, that usually suggests, depending on what direction the current is, that you're automatically oxidizing or reducing some kind of species. And it's already doing it. Let's see. So it's saying sulfuric acid electrolyte and carbon-rich electrode. So carbon-rich electrode. I'm going to post this here so we can see. So, okay. So one thing that could be happening if you have sulfuric acid, depending on the concentration is actually going to be very important. Okay. So the potential of your redox system will shift for every 1 pH unit, it'll shift by 59 millivolts. So if you by chance use a 0.1, because I think a carbon-rich electrode, there's nothing particularly special about it. But if you have like 0.1 molar H2SO4, and you do one experiment, and then you decide like, I want to use 1 molar H2SO4. It's like, well, that's going to be a 59 millivolt difference. Or if you just so happen to have a 0.0001 molar, right? And then you switch to this one, that's going to be maybe a couple hundred millivolts in terms of the difference. So that could definitely happen. There may be something, if you have a platinum counter, but also keep in mind that your reference electrode potential may have shifted. So if your reference electrode, if you were using silver chloride, or more likely you're using some kind of chamomile electrode, and for whatever reason it's not stable, or the salt inside of the chamomile electrode changed, the concentration of sulfate ions changed, then that might shift your potential over. And when you start at 0, you're actually starting maybe more positive, a little bit more negative than you really think you are. So those are all things that could be the reason why you have this huge current at 0, is because the thing itself could be oxidizing or reducing at 0, or your reference electrode potential has shifted. So those are a couple of things to think about. And I hope that this was helpful. This maybe gives you a little bit of insight into what might be happening. Okay, so, and of course, if you have further questions, for everybody, if you have further questions, please let us know. Further clarification, we're happy to help. Race Bannon had a question. And if we skip you because we're just going through the chat, trying to answer things, Race had a question, which is, I'm getting a charge transfer resistance in the range of 10 to the minus 5 ohms. What could it mean, and why this low value where I'm having these low values. I usually see the literature RCT is 10 to the 3. And Neil, are you having connectivity issues? Maybe it's just me.
No,
No, you're good. Okay,
no,
all
I'm
right.
good. Sorry, I was working out. There was another question. I was trying to.
All good.
Someone asked about different densities of stuff.
Sure.
I have some
No, I was just
data to show, but I was just kind of working out a thing.
yeah.
Yeah, Race, I guess you're talking about battery stuff. And so
So these kinds of resistance values are very low, and
yeah, that's quite a low. In fact, 10 to the minus 5 ohms is 10 micro ohms. That is close to the lower limit of what an average potentiostat can actually physically measure. Like if you take the leads of a potentiostat and you short them together and you measure the resistance, you're measuring like the intrinsic lower limit of the instrument itself. And it's usually micro ohms, some amount of micro ohms. So it means one of two things. It means you either got a severe error in your data caused by any of a number of different things, or you have a short and you're actually just measuring the resistance of your instrument itself, which is a big problem, of course, if you have a short. I suspect it's the former, not the latter. I suspect that this is just some sort of artifact of the data, some kind of odd error, and exactly what it is unclear. Right. I don't know. There's a lot of ways that something could go wrong. The way you have leads connected, and the way that you've got things, your parameters that you're trying, but almost no battery is likely going to have micro ohms of resistance or impedance associated with it. Milliohms, absolutely, but not micro ohms. That's so incredibly low that it's not reasonable or likely very possible with everything we have at our disposal for making batteries. It's not really possible to get impedances that small. I might be wrong, but that's my understanding. So I would take a look at your setup and see, because I think there's something probably amiss with your setup or with your parameters or something that doesn't sound normal, right? That is certainly too low. Let's see. There was a question.
Yeah, let's keep a look at. And thank you, Chris, also for answering and talking to people through the chat. It's very, very helpful. And your insights are always extremely helpful because sometimes it's like, oh, we don't actually know that much, or you actually give us some suggestions like, oh, I didn't even think about that. That's actually a really good question.
Cataline was asking about this is where it is. I couldn't find it.
Oh, okay.
In literature, there's a lot of equations evaluating the energy and power density. Can you tell me the right ones? Yeah. So the best I can do is try to share, like, for example, power, how you get a power curve. To be honest, I'm actually a little fuzzy on the energy part of it. I can kind of talk, but like if you have a polarization curve or a linear sweep, for example, this is like potential and current. So normally you have it CV, it's the opposite. But for a polarization curve, you typically put potential on the y-axis. You just flip the axes. The power curve, and this isn't density, I'll talk about that in a second, but basically the power curve is just multiplying them together. So volts times amps equals watts, and that's power. So the power itself is basically this. It's just the plot, and typically you plot power versus current or whatever. So you're finding the power density. So the density just comes from you would just divide all these values by your mass or your area, whatever the specific, right? So you said by mass, I think later, but basically sometimes density means by area. So you'll have, like, if you have this current as milliamps per centimeter squared, then when you multiply volts times milliamp per centimeter squared, you get milliwatts per centimeter squared, and that's power density by area. If you have your current in milliamps per gram, then when you multiply these together, you get power in milliwatts per gram, right? So it's just, there's no need to, that's just a very simple thing. You just, however many grams of your material you have, you just divide that by, and that's your specific power density. And so typically when people report fuel cells or devices what they do, the sort of the way the nomenclature is it'll be like, see that how this power curve, this blue trace has a maximum, is you report the maximum. So you're reporting the maximum power density would be this number. And in our case, it's whatever, 24 milliwatts. And if it was 1 gram, it'd be 24 milliwatts per gram, or 1 centimeter square, whatever, right? So whether it's just the raw power or it's the specific power, usually plot specific power so somebody else can relate to their mass of material. The energy is a bit confusing to me. I don't 100% know the best way people do energy, right? The conversion between energy and power and volts, right? It's joule. What is it? A joule is a volt times a coulomb. So something like, energy is like, the change in energy is the delta V times the charge. So it's like if you have a certain amount of coulombs that you've passed over time, that's associated with a drop. Sorry, let me draw this out. I'm just like pointing in midair frantically. I'll try to. I don't 100% know. So take this with a little bit of as this is the best that I kind of understand. It's just I don't know exactly how the energy density is calculated. I'd have to look into that a little bit as well, but I don't actually know 100%. But like the conversion is, so energy, if I use U is usually energy. So like the delta U change in energy is charge, usually Q, times delta V, because basically volts times coulombs equals joules. That's the unit conversion, right? Yeah. So something like if you have a cell where you just like if you have like a current and you have a voltage over time, and you measure like some amount of current over time, then that integrated, that's the charge, right? That's your charge or whatever. And let's say your voltage started here and did this. I'm kind of making this up to some degree, to be honest, because I'm not sure if it's exactly what's done. But in theory, this is the right equation. Like you have a delta V here of this, and so you can technically you can plug those in and get an energy. And if this if your current here was by mass or by same argument as before, you have some amount of milliamps. But if this is milliamps per gram, then this is like coulombs per gram, and then you get energy density, which is like joules per gram or whatever. Okay, so something like that. But exactly specifics, and if that's exactly how it's done, it might be a slightly different calculation, and I'm not 100% sure where and how the like calculation comes from for energy density of a cell. That I'm actually I'm a little not perfectly clear on. I might be off exactly on how that's calculated. Yeah. So take that for what it's worth. I might be off, to be honest.
It's all good. Some of these questions are complicated. So there's a question. There's actually 2 questions from Nikunj. I hope we're getting that right. So under what conditions is the E naught of a cell equal to 0? And I guess delta R GO or G, maybe that's supposed to be G. I think these are all G naughts equal to 0. So the E naught of the cell. So first off, the potential is a relative quantity. So the potential of a cell in some cases is defined by its relative position to another thing. So whenever you read in the literature or in a textbook, like, oh, this reaction has a voltage that's E naught is equal to 1 volt or something like that, that is with respect to a known quantity, like basically like the SHE, the standard hydrogen electrode, because we decided somewhat arbitrarily to make the hydrogen electrode 0. We just decided. So
I didn't decide that.
I didn't decide that. Yeah,
Somebody else did.
somebody else did.
Don't blame me.
I don't know why they also picked the most complicated one, because there's like, it's like a 2-electron transfer process. So like, not only is it like, why don't you at least pick a 1-electron transfer process to make the potential? You had to make it 2, so it's even more complicated. So there isn't really like a, in some cases, everything has a certain type of potential associated with it fundamentally. Whether it's accessible or not is a totally different question, or whether it's useful or something like that. So, but the other thing to keep in mind regarding this type of question about relating the E naught of a cell and like the delta G of a cell has to do with the concentration, and my favorite equation, the Nernst equation, right, which relates the potential of a cell equal to which relates the potential to the E naught of the cell and the change in concentration. So one way to consider a condition where E naught is equal to 0 is when the change in the, well, let's do a little bit of math. There's another way we can think about this. So if we go here and I delete all this stuff.
You left the sulfate.
Left the sulfate.
There's sulfate
That's
around.
that's dead.
Get rid
Okay.
of the sulfate.
So now I always feel like this never catches. So the Nernst equation roughly takes the form of the potential is equal to E naught, the standard potential. Sometimes it's plus or it's minus depending on convention, but it's like NF over RT, something like that, times the natural log of the concentration or the activity. It's actually the activity, but let's just do concentration of like the oxidized species over the reduced species, right? So it's something like that. So then you may say, all right, well, the condition where E naught is equal to 0 would have to, is equal to 0 would have to be the case where, well, if E naught is 0, it's when the potential is equal to like this whole thing. When the potential is equal to this, and that means that the concentration of these things directly align with it, that's when you have a condition where E naught is equal to 0. So that's another way to think about this type of question is when you get this, when E naught is equal to 0, these two things, the potential and this, are equal to each other, right? Because that's when E naught is no longer part of the equation. So that's another way to think about it. The question is now, all right, well, under what conditions do you do that? Most of the time, people they want to know what this value is. So this is what we measure. We can measure this value. And so if we can find a situation where the concentration of these two species, the oxidized and reduced species, are equal to each other so that the natural log of 1 is 0 and this cancels out, then we can use this measured value to determine what E naught is. So that hopefully is a way you can determine what E naught is and when E naught is equal to 0. Now I think you had another follow-up question. Hopefully this was helpful.
I think the other thing I was just thinking, so to your point about the natural log being 0, I think that the answer, at least an answer to this question, is that when the concentration of technically the activities of the reagents are equal, that natural log term goes to 0.
Mm-hmm.
And that means that your equilibrium constant is 0, is unity, which makes the natural log of unity 0, which makes the right side of that equation go to 0. And that makes delta G equal to 0. So it's basically, it's not equilibrium. It's where the activities of both sides are equivalent.
Yeah.
So the short answer to your question is where the activities of the reagent and the product and the reactants are equivalent. Your delta G is 0 and your Ecell is also 0.
Yeah. And your equilibrium constant's 1.
Right. Right.
So
Yeah. The question before that,
Something
he said
like that.
said something like the absolute potential of an electrode, which you already answered. Basically, there isn't one.
oh yeah,
It's all relative to hydrogen.
It's all
There
relative
is
to
no
hydrogen.
absolute potential.
Yeah.
It's not. There is no such thing as absolute potential. Potential is by definition a relative concept.
Correct. Yes. Nikunj also has a follow-up, so I just want to hopefully answer both of Nikunj's questions, which is, why is alternating current used to measuring resistance of an electrolytic solution? And this can go into a whole can of weeds and things like that, but I would say alternating current, really actually more like alternating current, alternating potential, electrochemical impedance spectroscopy in general can be used to determine the solution resistance. And part of that has to do with capacitors, of all things. It has to do with capacitors and the nature of impedance itself. But if we kind of delete that, I can go over this kind of quickly. But if we model, so if we say that our working electrode is here, actually, sorry, I'm gonna change this, just kind of what I'm used to perspective wise. If your reference electrode is here, let's say your reference electrode is here, this point. Typically, you'll have some kind of solution resistance, and then you'll have charge transfer resistance at the working electrode surface, in parallel with a capacitor that represents the charge transfer, that represents the electrical doubler. So you're working electrodes here. This is the model, a Randall circuit, that's commonly used to determine for measuring the solution resistance. So this is solution resistance. That's what we're trying to solve for. There's a unique phenomenon, and I don't have the equations in front of me, but when you alternate, when you have a sinusoidal potential or a sinusoidal current, the impedance at for a capacitor the impedance of a resistor, alternating current, is actually independent of frequency. But the impedance of a capacitor, this guy here, is approximately equal to like 1 over j omega c, where c is the capacitance and omega is the frequency. So and this is all related to the impedance z. And so as the frequency increases, the impedance decreases. And what some people do is they will do a very high frequency EIS experiment between their working and reference electrodes. And when they do that, this becomes the path of least resistance. And so the electrons at the sinusoidal wave will move through this solution resistor and then through this capacitor, because this guy may be too high to your working electrode. And when you measure the resistance in the high frequency regime on a Nyquist plot, you get something that looks, let's just say, something that looks like this. And the distance between 0 and this high frequency point is representative of your RS, because this is the x-axis is the real impedance, and the y-axis is the negative imaginary impedance. So I'm going to just write this here. And then this is kind of Z real, as we call it. And so this is one reason why a alternating current or an alternating potential is used to measure the electrolytic resistance. It's to get this RS value, the high frequency impedance through a capacitor gets very, very small. So much so that you can estimate, this value here is the resistance. So that's kind of the nutshell answer to why an alternating current is used to measure the resistance of an electrolytic solution. And I think those are all the questions from Nikunj. So if you have any further questions or you need additional clarification, please let us know.
I want to also comment AFSI analysis. You're talking
Mhm.
about which reference electrodes to use. This is a separate conversation. Chris, you're basically answering it for us. And I know you talked about it.
Mhm.
Yeah, you have basically sulfate. You only have silver chloride and mercury oxide, neither of which are really applicable for a sulfuric acid solution. Try a salt bridge. Was that mentioned? I don't know if that was mentioned.
No, that wasn't
So,
mentioned. That's good. That's a
so
good point.
in short, if you have to use, and I know you, and I'm a little, I've been looking at other questions, and so I'm a
Yeah.
little perhaps out of this loop. Let's just say, I was just going to note that if side reactions is some other problem, and this might not be exactly what you need. But if you have your main solution, and you have your working electrode, and you have your counter electrode, and you have your reference electrode, but instead of putting your reference electrode in here directly because you don't want chloride, if that's the problem, and maybe that's not the problem. So again, I'm not sure. You can use a salt bridge. So you put like a probe in here instead of the reference electrode. It's basically like a tube that goes to another cell that's separate. Oh, this is a really bad drawing. And this is where your AGCL reference electrode would go. Okay. And so basically you fill this with whatever you want, basically, because now there's an interface between your sulfuric acid here and whatever this electrolyte is. Instead of having this be KCl, because that's what's in here, right? Inside your reference electrodes KCl, and you're trying to avoid having maybe chloride or something contaminating. Okay, so you can put something different in here, more sulfuric acid, whatever you want. Basically, you're separating your reference electrode some distance physically from the cell. Can help with contamination.
Yeah.
So that's just one suggestion I want to make about that. And then I wanted to also, there's a follow-up here. Chatelier Paul, yeah, an example of an equation. I think I can actually speak to this. E equals 1/2 C delta V squared. So let me just share one silly little thing here. It's actually something I use myself from time to time to remind myself of these unit conversions. So go to the Wikipedia page for farad. Okay. So I find this to be really helpful. What I'm showing right here. And I copy it, and like this thing.
Oh, yeah.
This long list here. This can help you see where stuff comes from. There's probably a similar one for Joule or something, I guess. But this one here. Okay, let me just point out a few things. So the expression that I drew before was like Joule is equal to, what did I say? Joule equals coulombs times volts. So look at, I can't draw on the screen. You know what I'm going to do?
I'll just
I'm gonna do a fancy little thing here for you.
okay.
Hang on, bear with me for a second. I know you probably can't see exactly what I'm doing. You don't have to. Okay, I'm gonna do a thing. Just give me a second.
Yeah, it's
all's
good.
I hope this will be helpful, because this honestly, this is what I do a lot of times to remind myself of these silly unit things. All right, hang on one second here. Stop sharing. Share back my PowerPoint. So here's this, like, this is like the unit conversions. Okay, so what I'm trying to point out is, look at this and this. These are equal, right? Cancel one of the volts. Joule equals coulombs times volt. So these are just units. Forget about the expressions for a moment. Just do unit conversion. Joule is equal to coulomb times volt. What's another one that we can write? Right? As it relates to farads. Farad, I should use a different color. Farad is equal to joules over volts squared. So that means that farads times volts squared is equal to joules, unit wise. Now the expression that you told me was E, which is joules, is equal to, there was a 1/2 in there. I don't exactly know why. Okay. But capacitance, no, again, this sucks. Sorry. I'll put SP for space charge or something, whatever you put. SC, right? You put SC for like space charge capacitance, not to be confused with coulombs up here. I hate that we use the same letters for the same things. Okay. But I'm just trying to make a point here. And you put volts squared, right? This tracks like dimensionally. So the point that I'm trying to make here is that I think there isn't necessarily one answer. So what I suggested to you, where you can maybe get a charge, right? But this is coulombs. You can get a Q charge, whatever you want to call it, integrated current over time and multiplied by the change in voltage that gives you energy. You can also, if you can get a measure of the capacitance from like an impedance measurement or that sweeping back and forth like I talked about earlier, you get a measure of your capacitance, F. Technically, F times V squared is also energy. So these are the same things, but just calculated different ways. Okay, so this is the point that I'm trying to make. And the point about the 3.6 or 3600, that's just a unit conversion. Typically, when you see something multiplied or divided by 3.6 or 3600, what that refers to is actually the number one, 3600 seconds in 1 hour. So all that's doing is converting, for example, if I have coulombs, that is equivalent to amp times second. That's what that is, right? An ampere is a coulomb per second. So this is what people do in the battery world. Weird folks in the battery world is they take a coulomb and they divide it by 3600 seconds. Sorry, there's an extra zero there. Per hour. Seconds cancel, and you get amp hours. So this might be a similar thing. You might be if you multiply or divide, I guess it's probably divide by 3600. One side, I'm not going to exactly give because I have to think about it a little more heavily than I am at the moment, to be honest with you. But if you do that, you'll probably get something like joule hours or something. I don't know if that a unit that people use, something like that. But that's probably what that is. 3.6 or 3600 is just multiplying by unity. It's just a unit. It's a unit conversion. That's all it is. It's converting. That's like kilowatt hours, right? That's what that is. It's like kilowatt or watt hours or whatever. Sometimes you'll have per second, and you just multiply by 3600 to get the hours in the numerator. It's just a trick. Okay. Mm-hmm. So that's all that's where that comes from, almost certainly. Okay. So in other words, there isn't any difference, like fundamentally, from the equation, whether it's multiplied by 3 or divided by 3600 or not. It's just a unit. It's just a difference in units. So whether you're expressing something in amps or amp hours, or coulombs or amp hours, or like the equivalent for energy, whatever that is. And again, I'm not 100% clear on that, so I don't know. But the point is, that's a unit conversion. So it's the same thing. I don't know where the 1/2 comes from exactly, but I just showed you hopefully dimensionally how those are consistent, and that does work. So hopefully that's a little bit clearer.
I'm hoping to get a little more clarification on Kunj's question, but because I don't know what the unit is for something on the dilution. Acetic acid. Actually, I forgot what kind of acid.
Is that acetic acid?
No, it's two C's. I think that's
acetic acid.
That's acetic acid. Yeah.
CH3. Yes.
But I don't know what that unit. What is the
delta M?
Delta M.
Why on dilution is the delta M of acetic acid increases dramatically, while that of basically sodium acetate increases gradually? Dilution, the delta M. Yeah, what's delta
I don't know what
M?
delta M is. Or arrow M.
So hopefully, do you mean the molarity? I mean, literally the concentration.
I mean,
I doubt.
No, it's.
Yeah, I'm not exactly sure.
I need to know what that unit is.
I mean,
if it's resistance or if it's something.
Yeah, basically, you're diluting acetic acid versus sodium acetate, and something is. One of them changes at a different rate than the other one. Yeah, I don't know what you're referring to exactly. Yeah. Please clarify if you can. Yeah. I don't understand what the question is exactly. The only molality or molarity, I guess. Little m is molality. I think you're right. Molality. That's a bizarre concept. I learned about it forever ago. I don't know if I remember.
It still all has to do with like the concentration, and there's
total moles of solute. It's moles per kilogram. Yeah, it's still a concentration.
Still basically. A concentration.
Moles of solute per kilo. But molality is moles of solute per kilogram of solvent. But it's the same mole concentration.
Yeah, I'm not
Moles
so
of
sure.
solute per kilogram of solvent. I don't know if this is an activity thing. Is there a difference in activity between sodium acetate and acetic acid?
There could be.
Yeah,
Definitely could be.
I don't know, to be honest. Maybe
Yeah, I mean,
it might be that sodium acetate also dissociates slower.
it should dissociate
But it should
quickly
be
in
quickly.
aqueous
It's sodium
solutions
salt. Yeah, I don't
compared to like a weak acid like acetic acid, which is
Yeah.
strange because it's like you would think like, oh, well, the thing changes or establishes equilibrium faster. So why does the change
molarity.
happen? It's molarity. Okay.
So you're saying the molarity changes quickly for acetic acid, but not sodium acetate? Increase on dilution. On dilution, the molarity of that increases. First of all,
Well-
diluting, you're talking about the increasing. When you dilute something, the molarity decreases. So I don't exactly understand.
So
the
the
question.
so like the molarity should be decreased. Oh yeah.
Yeah, the
the
molarity is
person said-
decreasing as you.
So why does it change? Yeah. So yeah, you're right. If the molarity should be decreasing and one's increasing, decreasing, only thing I can think of is you have a buffer, because acetic acid is a weak acid, and if you have some kind of buffer system, then
Yeah, buffer is
well,
the salt of a weak acid plus a weak base, or
yeah,
basically
yeah,
something
and it's
like that.
and it's conjugate base. Yeah,
don't
this
know.
weak acid plus its conjugate base. I'd have to see a little. Oh, not acetic acid is a weak acid versus a salt. Yeah, it's there's a little bit to understand. Maybe there's parts of the question that that might, because it is a dilution, it should be decreasing. So is it decreasing or increasing? If it is increasing, something's weird. So so maybe Nikunj is kind of figuring some of that out, and but in the we can wait for Nikunj or someone for him to respond, or if you wanted to get to.
Yeah, we'll get to the next thing, I think.
Yeah, because Race has a question. He may just send us.
Oh yeah, you're gonna send me
some
some data,
results.
perhaps I can look at it. But you came across direct current EIS. Well, that doesn't make any sense. What the hell is direct current? EIS is AC. What's DC? DCIS. That doesn't make any sense. I don't know what that is.
direct current EIS DC. Yeah.
There are no advantages because I don't know what it is. I don't know what that is. Direct current. Yeah, that sounds
Yeah.
like a contradiction. Direct
Yeah.
current EIS. I've never heard of that. Nothing's coming up when I search for it.
Yeah.
I mean, the only thing that I could think you mean
Pulse
is
DC.
doing impedance at a set point, like having a direct
Yeah.
having a baseline.
Yeah.
Like the DC aspect of it is your set point, and you're doing EIS on that set point. And that's just EIS.
Yeah. Wait. So
Or
Race Bannon
if
just
you're
said
answering
yes.
pulse DC. So you're actually just talking about pulse methods and not EIS.
Pulse DC. Okay. Yeah.
Yeah. Okay. So if pulse DC. Okay.
Okay.
Yeah. I mean, so it's not necessarily advantageous to impedance. It's actually a different method.
Yeah.
The analysis is different. You can't do the same kind of analysis like circuit fitting and those types of things. It's a DC technique, right? I mean, you're pulsed, and actually I should clarify, because there's different types of pulse techniques. For example, you might pulse like up and back, up and back, up and back from the same 2 points. Sometimes you're doing that to like create a gradient in concentration. You're doing that to create a surface condition. You're doing that to test a diffusional component. There are different reasons. And sometimes you do a waveform where you move gradually up or down while pulsing, and you're subtracting the forward and reverse currents as a means of background subtraction that can clarify peak positions. For example, differential pulse voltammetry is a way to, in many cases, it's better than cyclic voltammetry because it can really clarify peak location. For example, you get the same peak on the forward and reverse scans because it removes background processes. And so anyway, that's probably not what you're referring to, because if you're talking about a pulse, DC pulse thing that's analogous to impedance, it isn't really the same thing. I don't really even know what the analysis looks like for something like that exactly. If you're doing it the same way where you're pulsing while changing the frequency of the pulse, and you're doing it in an analogous way to impedance, but it's not sinusoidal, it's just pulsing. I mean, it's interesting. I don't know how the analysis compares, to be honest. But yeah, it depends on the pulse shape. That's what Chris is saying too.
Yeah.
There's a lot of different kinds of pulses you can do. And again, there's different analyses, because whether you're subtracting a current of parts of the pulse, or you're just taking the positive pulse characteristics or something, like there's a lot of possibilities here that could be anything, I guess. Yeah, I don't know if FFT would work exactly. FFT is fundamentally FFT fundamentally requires sinusoidal. Maybe it works with something like a DC pulse, but I would assume FFT would require a sinusoidal input. That's usually what FFT uses. Maybe, I don't know if there's another kind of Fourier analysis that would work. I mean, that's an interesting proposition, but it seems to me like the analyses are really actually quite different. Just fundamentally, impedance analysis is like what it is. It's the sinusoidal Fourier transform into complex plane. It's how you get Nyquist plots, and then you can circuit analyze. Like that's kind of that world. Anyway, lithium ion battery real-time diagnostics with DCIS. I could try to find
something
that
to look for. There was a question earlier by Rajavarman, which is one of those opinion questions, which is, from your point of view, electrochemistry is saturated. Which I guess it's like, okay, is electrochemistry saturated? What does that mean? But I would say generally, I don't know, my guess is to say no. There's a lot of need for more electrochemistry. I would say electrochemistry also is much more of a tool nowadays than a fundamental study itself. There are still a lot of people doing fundamental electrochemistry research, but a lot of people are using it to study batteries, fuel cells, solar cells, corrosion. There's a myriad of applications, as well as just biosensor work. So I don't consider it saturated. I think we need more people doing it, sort of say. There's a lot of research and a lot of things going on related to it. So that's kind of my 2 cents.
I think it depends what you mean by saturated. Like,
yeah.
Is there, it's such a, try to choose my words carefully here. It is probably not true to a very large degree, but as far as my somewhat myopic understanding of the field, I would say you could consider the term saturation as far as the subtopics of electrochemistry are concerned, like fuel cells, batteries, supercapacitors, spectroscopy, spectral electrochemistry, photoelectrochemistry, general electrocatalysis, right? Like you could like biosensors, like you could come up with like a list of like 10 to 20 things. I don't know. Come up with a number, right? And like that list might be saturated, or like mostly. So like, just to be fair, right? Like, is there a brand new thing that like electrochemistry can do that we don't know about? I mean, for sure, maybe, but it seems
fusion.
Cold fusion, exactly.
Right.
It seems less likely now than like 70 years ago, Like 70 years ago, we didn't know anything about batteries, basically, other than the voltapile, whatever.
Yeah.
Pick maybe not 70, I don't know, 100 years, whatever. Pick a number, right? My point is, like, from that perspective, maybe. But within each of those, there's like always and like basically forever a permanent unsaturation, because there's always more stuff that's being discovered, learned, technology being improved, incremented. Now, whether those increments are as dramatic every single time, of course not, right? Like, we don't go from a battery that can keep your phone alive for a day to a battery that can keep your phone alive for 9 years like at all, right? But like, the idea of having a phone that I can carry around in my pocket and it'll stay alive and I can do all kinds of crazy things with it all day and not have to put any energy into it, like 20 years ago, is like insane. Maybe I don't know, how old am I? I don't know, whatever, like 30 years ago. My point is that, like,
Yeah.
we've improved a lot because there is a definitive unsaturation of knowledge that we in technology for what we can achieve in each of those kinds of things within electrochemistry and probably within every scientific endeavor to a certain extent, you know? And so I guess that's a optimistic outlook, because frankly, if it were, why are we all doing this?
Yeah.
And everything's so saturated. Why are you even going to grad school? Why are you even trying to join a company to do anything? Why is there even research at all? And it's like, I would heavily advocate for the continuation of research,
Yeah.
unsurprisingly to anybody.
Right.
Not just for my own company's health, but also just because it's the right thing to do as a human species. Like, I doubt and severely disagree with the idea, if anybody would have it, that electrochemistry, or really any scientific field, I shouldn't say that, I don't know everything about every scientific field, with that electrochemistry in particular is saturated. I do think that there's tremendous research that keeps going, you know, and that's a good thing. You know, we want to keep on discovering new stuff and you know.
Yeah. Just progress, just technology, all that kind of
Oh
stuff.
yeah.
All right. So there's a couple quick follow-ups. So just to answer, just raise this quick question. The Electrochemical Society is having they have 2 national meetings, one in the spring, one in the fall. The fall one is in October next week. Actually, I'm leaving there for in a few days. That's going to be in Gothenburg. I think it's pronounced Gothenburg. I think I'll find out when I get there.
Is it one of those, is Swedish a language where the th is like Gutenberg? You know what I mean?
Oh yeah.
Or is that like
Gutenberg.
that's like the printing press?
Yeah.
That's not
But
right. I don't know Swedish at all. I've never been.
yeah, I
I don't know anything about the language.
I just know the stereotype of the Swedish chef from the Muppets.
Oh,
that's about it. Just, just making the spicy meatball. You know,
they probably appreciate that in Sweden when you bring that up. That's
maybe.
that's probably what it's all about. Yeah.
Yes. Okay. So back to going towards some questions. So Nikunj mentioned 2 things. One, just kind of going a little bit back. Let's see. Acetic acid is a weak electrolyte. The number of ions increase on dilution due to increase in degree of dissociation. This can be gradual. This can increase gradually. So, so the molarity, the concentration, the molarity can decrease as you dilute it, because there's more salt. You can think of it as there's more solvent molecules per unit acetic acid, and how it dissociates. But you're right, it does dissociate, and slowly, based especially upon its equilibrium constant. So you can definitely do that, and that so you can think about the decrease in the concentration or the increase in the degree of dissociation is gradual, but you mentioned that this increase is fast by comparison to the acetate ion, the sodium acetate dissociation. So I don't know enough about that, but I think basically you can think about it and discuss it from that perspective of chemical equilibrium, and that, if you were to write out the equilibrium expression for the dissociation of acetic acid to protons and the acetate ion versus sodium acetate dissociating into acetate ion plus a sodium ion, you can look at how quickly that process happens and its degree of dissociation as being fast or slow. The equilibrium constant definitely helps. So, but of course, maybe there's a little bit of clarification. But that's how you should think about it, especially because I'm sure you're not doing research on this. You're doing research on something else, but you can at least use this information to inform your thinking about it.
Let me share a thing.
Okay. He has
sh-
another
I'm not
question. I was gonna.
Yeah,
But-
just to
but go
that
for it.
point though, you're talking about the equilibrium constant. So basically, one way you can think about this, right?
Mhm.
The acetic acid, I'll just do AC for acetic acid. HAC plus. So one way to look at it is HAC goes to H plus AC, but you can draw it with a hydronium this way, right? So that HAC plus water goes to hydronium plus acetate.
Yeah.
So to your point, it's that basically this is Le Chatelier's principle. As you increase water, you drive the reaction this way. So you're driving more dissociation.
Well-
So when you that's what you're referring to. You are diluting it, but you're increasing the dissociation of H and AC.
Yeah,
You're
it's
driving the equilibrium to the right.
Well, yeah, I would just my only comment is that because liquid water is a liquid, it won't show up in the equilibrium expression because the activity of water
Yeah,
will
that's
be
true.
unity. But just the concentration, because you're right, you are decreasing the concentration by increasing the amount of water. So you are in effect. So I would actually just write that arrow down on the AHC, and then how does that shift the equilibrium associate?
So it's if
So
the-
concentration of HAC.
yeah, the
goes down.
concentration of so that's actually a better way to.
That would be another way to look at it.
Why is this thing slowing down?
Oh no.
My PowerPoint died. That's what happened.
Oh, because PowerPoint died. Fun.
PowerPoint didn't know how to undo.
Thanks, Microsoft.
Yeah, thanks a lot. Oh, there it is. That came back. It recovered.
It recovered.
It recovered my scribbles. Thanks a lot. I don't want you to recover. I don't care. Yeah, no, I think you're right. Yeah, I shouldn't have.
No, it's
including water's unity. So that's not the right way to look at it. But yeah, you're right. I think you're right. It's the concentration of HAC goes down.
yeah, and as a result, it will shift the equilibrium to the left
yeah.
to the reactants to reestablish to reestablish the decrease in concentration. So yeah, when you okay, take that back just a little bit, because if we really think about this as a Le Chatelier's principle problem, then if we decrease the concentration, like if we have a solution and we decrease the concentration, we're decreasing the concentration of everything, right? So we're decreasing the concentration of acetic acid,
Yeah.
we're decreasing the concentration
hydronium.
of hydronium. We're also decreasing the concentration.
Yeah, so it's
of the
not
acetate
it's not
ion.
exactly decreasing. It's not like driving one way or the other, because you're decreasing everything.
Oh no, you will drive it one direction. It will drive in the direction.
Whichever one decreases less or whatever the
Yeah,
way to
yeah.
look at
So
it. Yeah.
so because you have more products decreasing in concentration, you will drive, and you only have one thing decreasing on
Right,
the other
it'll
side.
drive to
It'll
the
drive
right.
it to create more products.
So I drew the right way, but I had the wrong reason.
Yeah, no.
Okay. So that's
Equilibrium is
Yeah.
complicated in this way, and I only recently had to like think about this, so that's the only reason why I'm why it's like, oh yeah, it's like it's unity. Le Chatelier's principle works this. It's more complicated with gases, right? Like when you have gas phase equilibrium, it's a whole different thing. Not entirely, but and to kind of hammer the point, not hammer the point home, but to continue talking about general chemistry a little bit, we can answer Nikunj's last question, which is how is the Ecell affected by the concentration of zinc 2+ ions increasing? So again, this is you can do an open circuit potential experiment with you have two electrodes in your system. It's a 2-electrode system. You're measuring the open circuit potential, which is your potential of the cell. And if you were to increase the concentration of zinc 2 ions, you would look at the Nernst equation and the equilibrium expression, and then see how the zinc 2 ions shift the equilibrium. And then that will show you. So just to kind of, I'll just draw the, just the Nernst equation, just kind of one quick time. Hopefully you can all see it, but just remember, if you have so you have a cell with solution, you have kind of 2 probes and a voltmeter. Oops, voltmeter. Smallest voltmeter. And then, the E of the cell, which if you have a potentiostat, you can control, you can drive the potential of the cell. But if you're just passively measuring the open circuit potential of the cell, it's that E naught plus, I think it's like NF over RT something. I may have this part incorrect. I have to double check. And then it depends what your reaction is. So if you have zinc plus 2 electrons, no, you have or zinc 2 plus 2 electrons to give you zinc. Depending on what this reaction is, you then have the associated kind of the whatever goes in here is based on what this reaction is. So if you're throwing solid zinc into the solution, like for example, if this was it, then you'd have something like 1 over the concentration of zinc or activity, and then it's 2 plus here. 2 plus goes in here. And so this governs how the E naught of this, or how the potential of the cell is going to change. So now this assumes that this is the only reaction in this cell. So that means you need some pretty clean water, ultra pure water, very clean solution, and then clean electrolytes when you're adding this. Because let's say you had a tiny amount of ferrocene or some other species. Whatever species has the fastest kinetics with a reasonable concentration is going to govern the potential of your cell. So that's another thing to keep in mind. But this is how you would figure out, if I change my zinc ion concentration, how would it change the open circuit potential or the cell potential? Hopefully that makes sense. And Nikunj, let me know if you need further clarification and stuff like that. How are we doing?
I think we're okay. We'll
We're
try to
okay.
finish. There's a couple of pre-prepared questions I wanted to get to. We haven't gotten to because there's been so many live, which is great.
Yeah.
So Jahid asked, I would like to ask why in metals or ceramics corrosion increases with increased surface roughness. Basically, Chris answered this question. Surface area is higher.
Yeah, more sites.
More complex answer is lattice, blah blah blah. Basically, that's, I mean, the best answer to give is really that's it. So as the surface gets rougher, the surface area increases. It produces more nucleation sites for corrosion, which is an electrochemical process in oxidation, right? The surface is rougher, creates more edge effects. That's where corrosion is preferentially going to occur. It can cause a breakdown. If the surface is rough, it can cause a breakdown of passivation layers that might protect otherwise against corrosion, things like that. But yeah, basically it's relatively simple answer for that part. But let's see, there's a follow-up. I think Jahid says, I hope you discuss the lattice point in material and crystal structure will affect corrosion, how to explain increased surface area will increase corrosion. Well, I mean, honestly, that's it's somewhat of a self-explained phenomenon. Corrosion is an electrochemical process. Electrochemical processes are by definition surface processes. And so current is proportionate to surface area. Like more surface area equals more current. And by saying more current, we're saying more corrosion, because corrosion is an electrochemical process. Electrochemical process is a surface process. Higher surface area equals more current equals more corrosion. Like I'm just talking in circles, but I'm trying to stress upon you that the explanation is actually, it's somewhat of itself. As far as the lattice point, that's a different kind of a phenomenon that I don't know I can speak very heavily to. You know, for example, some materials have certain lattice structures or planes that are more electrochemically active than others. And I don't know how to properly explain the reason for that, really, to be honest with you, or at least in a very short amount of time. I don't know that I could do that. But for what it's worth, some structure with a lattice site that has a more elevated electrochemical reactivity will have higher corrosion, because corrosion is electrochemical, stuff. And then lattice defects.
Yeah.
Uh,
And active sites.
Defects usually are places where electrons are likely to go. It's a preferential site. And so it's like, when it comes to like electrochemistry, people sometimes intentionally add defects to their catalyst because it improves electrocatalytic activity. With corrosion, everything that you discuss basically as an electrocatalyst, someone studying electrocatalysis, is opposite. In other words, electrocatalysis, you're talking about, can I do stuff to my catalyst to make the current go up, to make the electrochemistry happen more? With corrosion, it's like, can I do stuff to make the corrosion go down? Because corrosion is the electrochemistry. It's bad. It's like the only situation. I shouldn't say it's not the. It's probably one of the only ones. I don't know, but it's one of the only ones where corrosion, where you're talking about an electrochemical process that you're trying to stop from happening. You're trying to make the electrochemistry be as low as possible, because those processes destroy your sample. They corrode your steel or whatever, right? So that's sort of the thought process behind that. But I hope that's relatively clear, that the surface is the current, is proportionate to the current. Hopefully that point is clear to you.
Yeah. Another thing, I'll just kind of I'll draw this very kind of quickly regarding like, I don't say I'm good with like lattice structures and all that kind of stuff, but some of the arguments or thought processes behind it. So like, yes, you have a larger surface area, so there's just more kind of sites. But if you think about like, oh, if I have all these like atoms here on the surface, and I'm not going to draw this a lot, and then I have atoms like, inside the, layers in between, then if I look at this guy right here, he's super stable because he's like bonded. He's getting great energetics from all his neighbors, stuff like that. But all the atoms on the surface, those are not as stable. They're stabilized by their adjacent friends and stuff like that. So when you have a lot of surface area, you have more exposure to these surface sites where things can happen. And additionally, this is just one part, but maybe you have kind of like ridges and hills because you have surface roughness. It's not atomically smooth, right? So this guy right here, holy cow, like this guy, he doesn't have as much like help. Like he's got more areas where it's much more easy. It's easier for like an oxidation process to occur, for a corrosion process to occur. So and similarly, you'll find like a hole where like, this guy's missing, right? That guy's missing. So now this area, these guys are now more electronically active to undergo a reaction. And so that's another thing to say about the stability. So and then surface area is just like, I have lots of these, right? Like I got all these, like I got these things, and I've got a lot of them, they're all over the place, here and here. Whenever I increase the surface area, I'm just getting more and more of this. So you get more current, you get more corrosion. So another thing to think about when you are considering why you have more corrosion, or understanding corrosion with respect to things like crystal structure.
So, Reyes, you asked my opinion on the mentioned article. So first of all, you've been watching me constantly since you sent it. I have not read the whole thing. I'm not that good. So I don't have a very strong opinion on it. I haven't had time to really read it or look into this phenomenon, to be perfectly honest with you. That being said, from what I can tell very shortly, what I'll tell you on this DCIS versus EIS is that one of the benefits it seems they purport for the DCIS is that they can obtain unlike impedance, you can obtain relaxation kinds of phenomena because, for example, as you go to some potential, you let the current sort of decay, and you go to another potential, the current will decay. So those are lost with impedance because you're constantly changing in a sinusoidal way. Now, the downside I see to this DCIS is that they talk about how you can probe a bunch of different phenomena by their time constants by changing the speed of the pulse. Well, that's exactly what you do in impedance as well. And they actually mention in this paper somewhere in the introduction here that I'm reading very briefly that one of the downsides to DCIS is that you're limited typically with DC methodology to like milliseconds or seconds. So you're effectively looking at hertz to low kilohertz as the fastest you can do. So if you're studying processes that are slower, probably it's perfectly reasonable because you can probe the time constants in the second range or millisecond range to seconds. But that's why impedance is really great because you can go to, kilohertz to megahertz to probe faster processes because time constants aren't always in the range of milliseconds. They're often microseconds or something like that. So for that reason, impedance is much more valuable and powerful to be able to probe those processes. But I can understand why fundamentally trying to go with a DC process compared to an AC process might be preferred. It's a little simpler. It's probably a little bit simpler to implement, like in the field, practically, for one reason or another. Maybe a DC at a pulse technique. So for that reason, it might be a little bit easier. And if there's any other kinds of analyses you can get out of it, perhaps that would be useful. So there was a couple of questions from Matt Biang, I think yesterday or 2 days ago, that I wrote down because they disappeared for some reason on the live stream. I always wonder why that. It's like the YouTube event is there, and like someone asks a question, and like literally like an hour before this event, so like 3-4 hours ago, the questions were just gone, and I'm like, they were there. So I do check the event, like we make this in advance, whatever, like Monday or Tuesday, as a scheduled event, and then I check it every day if you ask questions so I don't miss them, because I don't want to, someone asks a question that they thought of on Wednesday or Thursday that they want to either tune in Friday and watch the thing later, and then it's like the question goes away and we never answered it. I feel bad. I want to try to answer. So So Mapiang, who's asked questions before, again, I'm not sure if you're watching now or you'll be watching later, but thank you for the questions. Asked about the transference number for cations or anions, and basically using EIS or chronoamperometry, and effectively the method that you're referring to was the Bruce and Vincent method. So what I'll do is just share with you the paper you're referring to. And I don't have a ton of experience with transference numbers, to be perfectly honest with you. But this is the paper from which it derives, as far as I'm aware. It's called Electrochemical Measurement of Transference Numbers in Polymer Electrolytes from about 1987? Yeah. So it's by James Evans, Colin Vincent, and Peter Bruce, hence Vincent and Bruce methods. That's where it comes from. So we scroll all the way down here, and this is, I believe, the equation to get transference number. It's this one. And so what this is referring to is a situation that is, as best I can tell, a combination of impedance and chronoamperometry. So as far as how many methods there are or what are all the possibilities, that I don't perfectly know. But the best that I can tell, I'll just sort of try to walk through this as quickly as I can. So I just copied the equation into my little sheet here. So this is the expression from that paper. So it's something like this. You have current, you have time. Excuse me, not current. It should be voltage. Voltage versus time. I think, yeah, no, I don't know. It should be, it is current.
Yeah,
It should be current because it's
Yeah.
chronoamperometry. I'm just
Yeah,
trying to talk this through at relative. I don't have the most knowledge about this, to be honest, right? But so it's like if you have applied a chronoamperometry, you're sort of having a decay. So basically you have IS is I steady state. So that would be like whatever this is here. So this would be your IS, and I0. This would be whatever your initial current is. Okay. And then delta V. So you would basically do two of these. You would do like V1, and then you would apply a different voltage and something like that. It's so forgive me for the bit of the messiness here, something like that. So you do two different quick like voltages. So you have a delta V, V1 and V2, two different chronopotentiometries, and you do impedance at each of these too. So that's where they come into play. So it's something like you do a set point, you do a quick impedance experiment. You're also doing a set point and measuring the currents somehow concurrently. And then you go change the voltage and you do impedance again, because that's how you get your resistances. You want to get resistance here, and you want to get the resistance here. Something like this. I know I'm doing a poor job of describing, and I do apologize. This isn't my area of expertise, but it's something of this nature. And so I think that basically the answer to that question is something along these lines, that it's some combination of chronoamperometry and impedance, and you're measuring the initial conditions, like right when you apply the pulse or something like that, and then right when after some time, and sometimes that time frame appears to be like a day. Like, I don't know, maybe the systems require a really long time to reach steady state. So it depends on the system you're doing, I guess.
Yeah.
But because this paper is specifically referring to like polymer electrolytes, which I guess, or polymer somethings or whatever, they take a long time to reach steady state. So this is actually like done over a long period of time. But effectively, this was the method of calculating this transference number.
Mhm.
Okay, so that's what that is. Now, the very general thing that I can say about transference numbers is that, to be perfectly honest, so the definition, generally speaking, of a transference number is it's the amount, or effectively the fraction of
Mhm.
charge or current or whatever that's transferred by a certain species. So like if you have NaCl, if you have 1 molar NaCl, in theory, it's like 50% of the charge is carried by Na and 50% is by Cl, but it isn't actually that way. I forget which one. One of them is more mobile. Chloride's more mobile, or sodium's more mobile. I forget. One of them is more mobile than the other, so it's actually like 60-40 or something like that, right? So like the charge is carried more by one species than another species.
Yeah.
So it's an interesting phenomenon, and to be perfectly honest, I don't really know what it's used for. Like, it's an interesting, like academic and theoretical idea. Like, okay, I have this solution, and like some of the charge is carried by some species and some by another. But like, what is the benefit practically of me knowing what the transference number of some species is? I don't know the answer to that. Like, maybe you boost one species because it has a higher transference number or something, or you eliminate one because of some like, I don't know.
Maybe it's just for studying electrolyte.
Yeah, like if
how
it's,
do we evaluate the
if
electrolyte?
it's just if it's just a diagnostic tool,
Yeah.
like fine, like that, it's reasonable to have diagnostic tools
Yeah.
for their own sake, to some
Mhm.
extent, to compare things or whatever.
Yeah,
but I
that's
just
true.
I didn't really use this. I've never used this myself in graduate school or as a postdoc or anything, so I don't have the most knowledge of it, like, practically, and so that's kind of the best that I can give you, which is to say that it wasn't much at all. But at least that's the paper that it comes from, and as best I can tell, it's some combination of impedance and
Mhm.
chronoamperometry. I don't know if there are other methods, to be honest with you. I don't know that. That's the best that I can talk about. So
we got a question that came in from Mawish Salim, which is, can you please elaborate on the modes of she clarified modes of transfer in a 3-electrode system. She then clarified, yes, I'm talking about the modes of mass transfer. So there are 3 modes of mass transfer in an electrochemical system. We can talk about them. There is diffusion, convection, and migration. So diffusion is the motion of molecules. So all these have to do with how do molecules move in solution or in any kind of situation. But diffusion is the what I describe as the random motion of molecules. How do they kind of randomly, sporadically move around? Convection is the controlled motion. I kind of think of this as like physical movement. Things like stirring is a way of physically moving molecules. That's another mode of mass transfer. And migration is the mode of mass transfer. It's a way of moving molecules based on an external electromagnetic field. And so in typical 3-electrode systems, such as cyclic voltammetry, for example, if you have a supporting electrolyte and you keep your solution still, diffusion becomes the primary mode of mass transfer. It's just molecules randomly making it to the electrode surface to undergo an electron transfer. But then again, in techniques like a rotating disc electrode, you have a diffusion convection method where you are rotating the electrode and creating a vortex of solution, kind of laminar flow, to an electrode surface. It's a controlled form of convection, and you can get more current. In some cases, the modes of mass transport will limit how much current you're able to push in your systems. Actually, a lot of electrical chemical engineers use the rotating disc for that kind of stuff. And then migration, not too many people. I don't see too many people actually use migration as like, oh, let's use an electric field and try to just move molecules in an electric gradient. People,
I mean, I guess
do that.
I guess the definition of diffusion is a random motion, but another thought of it is that random motion will also go in the direction of like high to low concentration. That's not really migration though. That's more of like,
so that's still diffusion. Like,
yeah,
so this is
that's
a
still
weird.
that's not migration. Yeah, like nobody really talks about migration. It's like,
yeah,
it's the ignored form of mass transport.
Yeah. So like people add supporting electrolytes, and I've heard two arguments about like why can you remove. There's something called the Nernst-Planck relationship. It's this equation. It's big, that relates the flux of molecules to convection, diffusion, and migration. And we do things to our electrochemical system to simplify the Nernst-Planck
which
relationship.
we always get rid of the migration term.
We always get rid of the migration term by adding a supporting electrolyte. And there's several arguments about why you can do that. And
I think that's right. That's basically like, in theory, if you had like one ion in solution, migration would define the completion of the electrochemical cell or circuit requires that ions move from one to the other, because you have electricity moving in the external circuits. You have to have, so it's like if you add the migration of like one ion, that a field would move it, but the supporting electrolyte means that that's distributed throughout, and so it's not. It's something like that, right?
I have heard
I might not be
so
describing
many
it perfectly,
weird
but
descriptions of it. Like, so I've heard that. I've heard the shielding effect of the supporting electrolyte shields an individual ion from feeling that force. But I've also heard the argument that by adding supporting electrolyte, you've converted your electrolyte into a conductor, and conductors don't have electric fields through them.
Right.
The field is outside of it, right? If you have an iron bar or something, a magnetic bar, there's no magnetic field inside of it. It's outside of it, and that's where your iron filings move.
Now reconcile that with the reference electrode phenomenon. How there's a field that is the sensing point or whatever.
Yeah.
I don't know.
I still don't know where. I still don't fully comprehend what the sensing point for the reference electrode is. You're right. Yes, this is.
Well, I don't understand why it's where it is exactly. Phenomenologically, I also am confused by that, which is kind of funny.
Yeah,
because we use them all the time, and I don't really understand why.
Yeah, it's like, why is it the frit? Why isn't it like beyond the frit? Why isn't there always this big solution resistance?
And it's that other point that like at least once every 5 to 6 months, I run into Alex's office and say like, I figured it out. I figured out how we never have to use reference electrodes ever again. This should work. And you're like, oh wait, but what about? And I'm like, damn it, it won't work. We have to keep selling reference electrodes. I hate reference electrodes.
But what we have decided that if we sold thick glass reference electrodes, it would be better.
It's true. Yeah, thick glass reference electrodes would in theory remove the stray capacitance effect.
Yeah.
And that high frequency artifact that you're seeing when you use your impedance on your reference electrodes, thick glass.
Yeah.
It would solve that in theory. Or you just remove the reference electrode from the solution as much as possible. Don't dunk it in super low. That stray capacitance will go away. But I swear, one of these days, that's going to be my contribution to electrochemistry, and then I'm going to retire a millionaire. I'm going to find a way that we don't have to use reference electrodes electrochemically. Like, I'm going to figure it out. The science is there. I can feel it.
Probably
I can
true.
feel it. I'm so close.
Probably.
I get these
don't
harebrained
doubt it.
ideas. Like, what if we just put a wire here and we just do a thing? And it's, oh no, that won't work.
That'll make it complicated.
That won't. Yeah, no. I really thought I had it once or twice, and then we talked through it, and I'm like, oh, I'm an idiot. That won't work.
No.
It's so funny. It's like my random thing that I like keep trying to do for no reason. It's like if it hasn't been done by now, I'm not gonna figure it out. Like, you know what I mean? If it hasn't been figured out by now, then it's not a thing.
Yeah.
It's so funny.
Let's see. Mawish has a follow-up, which is, thank you. One more question is, how in qualitative analysis we obtain the single CV curve of mixtures? How in qualitative analysis
I don't understand.
we
this
obtain.
question.
So I mean, experimentally, if you have a redox system, a test solution of electrolyte and a redox species, you hook it up to a potentiostat, and then it sweeps the potential, and then you get a nice like peak associated with the redox species. So that's typically now qualitatively, you can figure out, you can see what really there's actually a lot of quantitative analysis with cyclic voltammetry. So I don't know if I would call it a qualitative analysis.
And I'm not sure what you mean by mixtures.
Yeah,
Like,
that's
mixture of what?
another question. Yeah, what mixtures are we talking about? Are we talking about multiple electrode species? You can usually sometimes identify like, oh, one peaks over here, one peaks over there. Then you have two different species, two different things. So
I wanted to address this other way. There's one other question. This was like, I think this is a comment on our last week's live stream.
Oh yeah.
Kansu Ilhan. It might be like Kansu Ilhan. I don't know. Yeah, sorry. Again, I don't know what the username exactly is here. But this person commented on our channel, said, can you talk about photoelectrochemistry measurement with your instruments? What techniques should you use to understand photoelectrochemistry for the samples? So, I mean, the short answer to this is the same experiments that you use to test everything else. It's just that people typically report things like photocurrent, and usually what that means is the current when I was shining the light. So like I had my cell, and then I shined a light on it and I clicked go and I got a CV, and then I turned off the light and then I did a CV again and it looked different. And so one of them had higher current and one of them had lower current. That's the photocurrent. So something like that. Yeah. Or I did like chronoamperometry or bulk electrolysis or impedance or whatever. So in short, the techniques you're using are basically the same. They're just electrochemistry techniques. It's just that by illuminating a light on your sample, on your electrolyte or your whatever, on something, you're causing some other process to occur, some absorption of the light that changes a species, that causes a radical, whatever. It does any of a million different things, right? I mean, Alex is the spectroscopist. I'm talking out of my butt right now. I have no idea.
I think that's all.
But that's basically right. It's like there are no special, in some sense, there's no special method that's a photoelectrochemistry method. It's just electrochemistry methods when you're shining a light. Right?
Yeah. And some people will have what a lot of people will do is they'll measure a photocurrent. So one thing is like you could maybe measure a photocurrent when you shine a light not in solution, but you may. I've been trying to talk and understand like metal oxide and semiconductor electrochemistry, because most people are using some kind of metal oxide or a semiconductor material to do a photoelectrochemistry experiment. So there's photochemistry just by itself. You have a semiconductor, it has a band gap, you shine light. If you excite at the band gap, you're going to generate a photocurrent. So then if you take that and then just put it in solution, you now have a totally different looking thing. And if you dope it with N-doped or P-doped semiconductors, you also have a different kind of picture of the electrode energy interface. And then again, with light, without light. And then the chemistry that's happening on the surface. There's so much stuff that's happening in those types of situations. But to Neil's point, The techniques are still kind of the same, except, if you want to do like Mott Schottky, for example, that's a uniquely semiconductor photoelectrochemistry experiment.
Yeah, I guess that would be the exception to everything I just said. There
yeah,
is one. It's called Mott Schottky.
Yeah.
Okay. Yeah. So
It
I
can be-
neglect.
it
I
can be
neglect.
big.
Yeah. Exactly.
Okay, so moving.
Yeah, we got to wrap this up pretty.
Oh yeah,
soon.
we gotta wrap this up pretty
But
soon.
there's a general question here that doesn't have a very simple answer. But yeah. So
yeah, from
Anil, yeah. What are the kinetic parameters and thermodynamic parameters in an LSV? I mean, it's a pretty general question. Kinetic parameters in an LSV. It depends. Are you rotating or are you not rotating your electrode? Yeah. So if you're not rotating your electrode, your kinetic parameters are buried. Right. If you just do an LSV on an electrode, generally speaking, that's just still sitting there, whatever, you have all the processes are incorporated into the result that you're getting. So for example, people do LSV and then they make a Tafel plot sometimes, and that's not necessarily appropriate because that's not all kinetic information. The kinetic parameters that are in an LSV, like buried in there somewhere, is the kinetic current, the Tafel constant, Tafel slope, the electron transfer rate constant. But how you get those is a lot of different kinds of analyses, like Levitch and Kentucky-Levitch analysis and things like that. Thermodynamics, like E. Like the E0 and things like that. We talked about some of that earlier, equilibrium constants and things like that. Like, this is a very loaded question. It's not like something you could just answer like, here's an LSV, here's how you get everything. It's
there is actually something I can just go to. I can hopefully help a little bit. So LSV, so if we are strictly talking about LSV, stationary electrochemistry, we can identify some of the parameters from a mechanism. So I'm hopefully sharing. This is electrochemical simulation software. We've actually recently just launched it. There's a website, Aftermath Live, where you can actually play with this. I'm not going to do a lot of playing with it here, but you can simulate a cyclic voltammogram. So all the cyclic voltammogram data that you get, LSV data that you get, can be replicated depending on what it is. So if you have a simple electron transfer process, there is the potential. There's the E naught, that's a thermodynamic parameter. There's the heterogeneous rate constant, that's a kinetic parameter. There's alpha, the transfer coefficient, that's also a kinetic parameter. And then you can get things like the diffusion coefficient, which we consider to be it's a mass transport, it's a kinetic parameter. Those are really for a single electron transfer process. Those are the parameters you can look for and get. If you add something like a chemical step, you can get a rate constant associated with that chemical step. And that's it. Those are the things for LSV that you can get. And of course, if you were to, that's just LSV. And of course, if you do what Neil said and you extrapolate upon doing things like Tafel analysis, then you start to get things that are a little triggering.
Yeah, and he says that when he's rotating. So yeah, so the rotating analysis of LSV is Levitch, Kentucky-Levitch, these kinds of analyses. That's a complicated topic. Of course, I've done a whole webinar, a 2-part webinar on that. The recordings for that are on our YouTube channel for Tier 2 members. And so you can join our YouTube members and watch those. I'm also planning to give that webinar again before the end of the year. I was going to do it. I'm not exactly sure when, probably November sometime. Alex keeps telling me to push it off.
Yeah, I keep telling you to push it off. I think it's crazy. We have too many. We have a lot of stuff to do.
But I want to do. I haven't done a webinar in a while, and I'm itchy. I want to do one. So it's a little less intensive than my EIS one, because the EIS one's 5 weeks, and it's a bit a lot. It's a lot to do. But yeah. So despite Alex warning me, I might still do my RRD one sometime soon. So Anil, what I'll tell you is that within the next 1 to 12 months, probably within the next 1 to 2 months.
Stay tuned.
Yeah.
And you'll find out when it is.
Probably by the end of the year, despite Alex's protestations, I'm going to do my webinar on RDE, RRDE, Levitch, Kentucky-Levitch, Tafel, a little bit of impedance. It's basically a whole webinar series on that. And I do the analysis with you live. I do some experiments live, and I do the analysis in an Excel sheet, and I kind of go through. It's quick, obviously, because it's a webinar, but it's basically all of these kinds of parameter extraction from LSV, basically LSV, CV, whatever, same thing.
Mhm.
So,
Yeah.
so that webinar is coming, I promise, at some point,
Stay tuned.
maybe. So that's going to wrap it up for us.
Yeah.
Because
yeah.
it's been like 2.5
But
hours.
2.5 hours. Yeah. Yeah.
And I need to stop talking for a very long time.
Yeah.
So,
But I will be out next week.
Yeah.
I'll be in Gothenburg. So if you're in Gothenburg in Sweden at the ECS meeting, stop by the Pine Research booth. You'll have a chance to talk to me and my other colleague. Our other colleague Tim will
Yeah.
be there, and you'll see our Equilibrium rep, our European rep Ziad, who's also an electrochemist. So you can also ask lots of questions.
and I'll see everybody next week. I should be able to do the live stream solo,
Mhm.
and it'll be very sad and very lonely.
Right.
But it'll be just me.
Yeah.
So anyway, thank you everybody, and thank you Chris again.
Yeah.
Very nice to see all of your words, not faces, but
All your smiling, all your smiling words.
Smiling words. Yeah. So yeah, anyway, have a great weekend, everybody, and I'll catch you all next week. Take care.
See ya.